All right, guys. Thanks for watching my video. This is chapter 1, section 1.1 about motion. So, a lot of physics 1 is concerned about motion, velocity, acceleration, things moving, and we want to keep track of that motion and be able to describe it. And we're going to start with linear motion in one dimension. That means things moving along the x-axis. So, just going in a straight line, we're just going to be thinking about things speeding up. So, acceleration, and then things slowing down, so deceleration, and then traveling at a constant velocity. Okay. And the thing about constant velocity is if you're moving at a constant velocity, you might not necessarily know that you were moving unless you looked outside of the window or maybe you heard the train car. If you've ever taken a train or even flying on an airplane when you're cruising in high altitude, you can't actually tell that you're moving. So if there's no acceleration, you won't actually know that you're moving. Oh, of course, my friend George the plant. He's from IKEA. He'll be helping me with physics demos. I'm going to do a lot of demos, better demos than this foam squishy. But all right, so we're going to be talking about motion and how to describe motion. So here we have this falcon. Peregrine falcons are amazing hunters. They often start up very high and they fold their wings in and they can reach speeds of almost 200 miles per hour and they strike their prey with amazing force and it basically kills them instantly. And they use their wings, of course, to provide the force so that they can fly. But here the bird is cruising at a pretty constant speed, and so if the camera's maybe taking pictures of 30 frames per second, right? So in even increments, right? Every say zero point 0.1 seconds, the camera takes a picture. We can see that that our bird here has it's basically moved by just about the same amount of time every time. This spacing between these lines is exactly the same. So that tells us that our falcon is traveling at a constant velocity, right? So that's how we could look at this picture. In the book, they do a lot of stop motion photography. So depending on what you see in the pictures, and you know the time increment between the pictures, then you can say something about its motion. Here's a skier going off of a ski jump. Okay, so he goes up in the air. So at first he's traveling upwards, and let's see, is there a line? Yes, we'll get the arrow key. So he starts off up here and he's going up this way, and then he starts to go this way, and then he travels down this way. Now, what's interesting about this is his Y motion is changing, but his X velocity, it doesn't really change that much, right? Actually, at all, right? Because there's nothing that would make a change. So if we just draw an arrow between each of these ones, right, his linear velocity is not really changing. Okay, so as he's traveling in X, right? So if I throw my starfish here over there, okay, so I've got this cool starfish. Okay, as it's moving, right, the velocity that it's moving this way isn't changing. Now, if you throw it up in there, it's going to go up and then it will come down. That is changing. So why changes? Because we have the force of gravity. Gravity is always pulling us down. There's always acceleration. There's a constant force. Okay, at least it acts like a force. Now, is gravity really a force? Uh, Depends on what you call force. Maybe it's a force, or maybe it's time and space being bent by matter. Okay, so but it acts like a force because since space is being bent, we fall into it. Okay, it's like imagine if a really big guy got on a trampoline and you were standing next to him. Okay, you're on that trampoline, you would fall in towards the smaller guy. Okay, so that's kind of like what it's like. You're standing next to somebody heavy on a trampoline. Their mass is stretching space-time. You will fall inwards. So is it a force? Maybe it's just the curvature of space-time. Anyway, that's for physics too. But for now, the motion diagram, okay, if we have a camera that takes pictures in regular increments, we can find its y and its x velocity. And in this first few chapters, we're just going to be dealing with one dimension. We're going to be talking about speed and velocity. On your car, when you drive, the speedometer tells you the speed. This is based off of how fast your tires are spinning, right? How much do they rotate in what period of time? It tells you the the speed, right? But speed doesn't have a direction. The difference between speed and velocity is one is a vector, meaning there's a direction, so you know how many meters per second it's moving and in what direction, or it doesn't have a direction. You just know the speed. Okay. Your speedometer, literally, it just tells you how fast your wheels are spinning. It doesn't tell you if you're going north and west, uh, what direction you're going. Okay. So, speed is called a scalar, and velocity is a vector because it has a direction attached to it. There's a little bit of trig, okay, but we're just going to be using uh, mostly these equations. This is pretty much all of the trig that you're going to need, a lot of it for the whole semester. Okay, now if you're a little rusty, okay, don't fear because I am here. We're gonna go through some trig. Okay, so maybe this is 1.1. It's a little bit of trigonometry. Okay, but trig is fun. Okay, and here's something I want you to do. Okay. So yes, and we're gonna do this a lot. Since you are sitting at home, okay, since you're sitting at home, I want you to basically go outside, okay? And it's really important that you do this because I'm gonna tell you this right now. Watching these videos is okay, but you need to live physics. You need to feel it, touch it, not just do the equations, okay? But you need to go outside, okay? There's a whole world out there. It's right in your backyard. Physics is everywhere. One thing you're gonna learn. The thing about physics is it's fun. I know you're thinking, oh gosh, why? Why am I in this summer class of hell? What have I done? No, it's not hell, okay? Because the world out there is full of physics. Look at it. There's physics in everything. And pretty much anything that you do that you would call fun is it's really just physics. Okay, so here's what I want you to do. I want you to go outside. I don't know what it is. Okay, I want a tree, something really tall. Okay, in your yard, and don't do anything where you'll get into trouble. Okay, so don't trespass or go anywhere you're not supposed to. Okay, but I want you to go outside, and I want you to find something and measure how tall it is without climbing it. You're not allowed to climb it, and you can't use an iPhone app. Okay, you have to measure how tall it is and not climb it and measure. Okay, and pause the video, go and do it right now, and then post it on Yeah, let's do post it on the Discord. Okay. If you haven't joined the Discord by now, join the Discord. You can put your names there. It's anonymous. Please send me your names though on Discord. Send me a message. Tell me your actual name so that I know you're participating. But you're welcome to remain anonymous on Discord. I don't care, but I want to know who you are. So send me your name on Discord. Okay. So go outside, find something that's tall, like a telephone pole, and measure it. Okay, so pause the video right now. I'll wait. You can go outside, man. It's summertime. Wait here. Come right back. I'll go do it too. What am I gonna measure? Oh, you know what? There is a telephone pole in my backyard. Let's give me a second. It's right over there. There's my swing set. Nobody uses it anymore. Oh, well, there it is. Okay, there's my telephone pole. Okay, I'm gonna, I'm gonna leave this on, and I'm gonna go measure. But don't cheat. I'm gonna get outside. I'm gonna measure the telephone pole. Maybe this isn't what you thought online physics would be, but I feel like it's really important that we touch grass. So I'm gonna go touch the grass and measure the telephone pole. Oh, hi there. It's Dr. Wisbey. I measured the telephone pole. I think maybe you watched. So how did I do it? Well, let's go through let's go through the math. Let's go through the math and I'll tell you kind of what I did here. Right. So we're gonna do a lot of this too. Got a 4K document camera here. So imagine here is the telephone pole. Okay. It's pretty tall. Okay. And yeah, there's my telephone pole. And so here is me, just a guy. And I'm like, geez, how tall is this thing? Okay. Well, kind of gonna do a little estimation because I'm not gonna walk, like, I'm not gonna climb up there. I wouldn't try and do that. Okay, so starting with my telephone pole, I took about I went to over here and it took me about 10 big steps. Okay, so and I know from before because I've actually measured this that if I take one step, okay, this is about 3 feet. Okay, from my foot to foot. If I take a big step, that's about 1 yard. Okay, now as Americans, we probably think in yards and feet if you're like me. Okay. And um usually in physics we want to do everything in meters. Okay. And there's a lot of reasons for that. Okay. Now, it turns out that basically 1 meter is 39 inches, right? And 1 yard equals 36 inches. Okay, so what we're going to do is we're going to basically say 1 yard is roughly equivalent to 1 meter. Okay, so that's a handy conversion that I like to do. 1 yard equals 1 meter. Oh, hold on, I gotta go. So let's look at how I did it and compare it to your own method. Um, there might be a temptation to use a an app or something to measure this, but it's much easier if you just use trigonometry. So, for example, if we consider an equilateral triangle, we know that each side of the triangle has the same length except for the hypotenuse, right? The hypotenuse is bigger. So here's my, if I draw this triangle where the telephone pole is the opposite side, and then we'll say that this side is the adjacent side. If it's a equilateral triangle, then these two angles here must be 45 degrees. This one's also 45 degrees. And then this angle has to be a right triangle. So that means that this angle is 90 degrees. If we add up all the inside angles of our triangle, so we have theta 1, theta 2, and theta 3, these all have to equal. So if we add theta 1 plus theta 2 plus theta 3, these all have to equal 180 degrees. Okay, and so let's look at our triangle. We have 45 degrees plus 45 degrees plus 90 degrees. Okay, those do add up to 180 degrees. So one strategy would be to make sure that you are as far away from the triangle as it is tall. And so this is what they did because in ancient times, people wanted to actually measure how tall the pyramids were, but it wasn't really practical to climb to the top of it. And so what they did was they waited until the sun was in the sky in a position where the shadow of things was as tall as the actual thing itself. So here's the shadow of my pyramid. Okay, here's the shadow of my pyramid. Um, this is my pyramid here. And so if you wait until the afternoon, at some point, your shadow is actually as tall as you are. And so what they did to measure the height of the pyramid was they waited till this time and then they measured how tall the shadow was. And that's how they figured out how tall the pyramid was. Okay. For a telephone pole, what I did is I took uh, a bunch of steps, and I know that if I take a big step, that my big step is about equal to 1 meter. And so I got to a place where um, I was about 10 steps away, and then I held my arm up at a 45-degree angle. So here's my arm, and I pointed right at the top, okay, up there. And so I know that I was about, if that's a 45-degree angle, then the base of this side has to be as tall as my, as the thing that I'm trying to measure. It is, okay? So if I was 10 meters away from here, and then my arm is about 1.5 meters off the ground, so I counted 10 meters away. So I was 10 meters away from there, And then my arm is about, 1.5 meters off the ground. Okay. And so this part was also, let's see, 1.5 meters right there. Okay. So if I took the distance over here, this would be 10 meters and then a little bit more because I wasn't, um, my height matters too. Okay. So I had 1.5 meters plus 10 meters. That gives me, I think my telephone pole is 11.5 meters tall. Okay, that seems pretty reasonable. But basically, I use trigonometry. Okay, so if I know the hypotenuse of my triangle, okay, and I know the adjacent side or the opposite side, I can figure out any other side of my triangle. So let's do a little bit of trigonometry now. Um, I think it's actually relevant. We'll go over it again, but basically you can use trig to do this. Okay, so let me redraw this just so we're absolutely clear. Because I know that sometimes trig can be a little intimidating if you haven't done it in a while. But that's okay. We'll go through it. All of the math that we need to do, I'm going to go through it and I'll make sure that we understand it. And I'm also going to do example problems. Okay. All right. So here's our triangle in general. And this has to be a 90-degree triangle or a right triangle. Right. And if I know my angle here, okay, let's say that this is my hypotenuse is 10 meters. Okay. And I want to figure out and let's say that we'll say this is 30 degrees here. Okay, I didn't draw a very good 30-degree triangle, but that's okay. Okay. Um, you should remember your trigonometric identities. Okay, we'll call the hypotenuse R, and we'll call this side of my triangle X, and we'll call this side Y. Okay. The most important thing is our good friend Pythagoras. Okay, we know that r squared equals x squared plus y squared. Okay, this is the Pythagorean theorem, and it's very important. We'll use this a lot. And interestingly, that's who the guy is on the picture of this class was Pythagoras. He lived on an island and he sort of had a cult in this Greek island. Okay. And you weren't allowed to leave the cult. You couldn't escape, and no one was allowed to talk about it. But um somebody escaped from his island and they actually took this with us. Okay, they took the Pythagorean theorem with them, and that's how we know what it is. Okay, so this person escaped from his island on this cult. That's a supposedly a true story, according to the ancient histories. Okay, but the one that we know is the Pythagorean theorem. He may have known other things, but we'll never know. All right. So this is important. Okay. And we've also got sine and cosine. Okay. And so we know that y, the opposite side, equals r times sine of theta. And that's this angle here, theta. Okay. So theta is on this side of my triangle. And then we've also got x equals r cosine of theta. Okay. And then finally we have um, y over x equals tangent of theta. Okay. These are very useful. We'll use them a lot in this class, and so you should definitely be familiar with these. And there's a few problems to help you review this, but let's do this example here. So we've got a triangle here with a hypotenuse of 10, and we've got an angle here of 30, and we want to know what x and we want to know what y is. Okay, so we can use our scientific calculator. Make sure it's in degrees. We're going to use degrees in this class. So every time we do it, we want to make sure that your calculator is in degrees. Now, when I solve a problem, I don't put in the numbers until I'm very close to the end. That's so I don't get confused. because I tend to make a lot of mistakes. And so don't put in the numbers till the end. But let's say we know the hypotenuse here. So R equals, let's say 10 meters. Okay. And I want to know, let's say how tall this thing is. Okay. My angle here is 30. So what I'm going to do is I'm going to say, okay, Y is going to equal 10 meters times sine of we said 30 degrees. Okay, so let me get out my scientific calculator. I actually normally use MATLAB. I'm going to use the one on my phone. Okay, but hopefully you have a good calculator. For the test, you're going to need to have a actual calculator. Okay, so let's type it in here. All right, so I'm going to say my hypotenuse 10 times sine. Nope, that wasn't it. So it's going to be, yeah, well, we could do that. Okay. No, my angle is messed up here. See, this is why you shouldn't use your phone. Oh, man. Okay. All right. So our angle is 30. So we'll say sine of that times our hypotenuse, 10. Right? And that's going to give us 5. All right. So that says that y equals 5 meters then. Okay. And now we can get, and that was over here. That was the opposite side. I want to get the adjacent side here. So we're going to do the same thing. We're going to say x equals 10 meters times cosine of 30 degrees. And I'll put this in my calculator. So we'll say we're going to say 30. That's my angle times cosine times 10. Okay, that's going to be 8.66. Okay, and now this would be a good place to talk about significant digits. Okay, so that's going to give us 8.66. Okay, now in the class, when you do the homework, significant figures are important. Okay, and you see on my calculator here, I have a lot of digits. Okay, a lot of digits. Really, those things don't mean a lot. Okay. And I'd say in this problem, 10 meters, I have two significant digits, right? If I had written the number 10.0 meters, then I could say basically, okay, this is like three significant digits or one because I only have one decimal place. Okay, but let's go with three. So for this one, let's say we have 10, and I'm gonna call that a significant digit. And so in my calculator, I get 8.66025. And if you put that in your in the homework, you're going to get it wrong. And so you would put this in as say 8.7 meters. Okay. But now we're going to check it. We're going to use the Pythagorean theorem up here to make sure that what we're getting here makes sense. And hopefully my calculator is not in radians. Okay, so what I'm going to do here, it seems reasonable. Okay, but I'm going to say, all right, um, let's check it out. Okay, so I know the hypotenuse is 10. Okay, so I'm going to have r squared equals, all right, and I'll have one side y here. I'm going to put in for y, so that's 5 squared plus 8.66, so 8.66. Now, when I do my calculations, you don't want to get rid of any of these digits as possible. So I'm going to put these in. I mean, you want to keep most of them if you can. Okay, so since I already got this on my calculator, I'm going to just square this one. I'm going to say give me that one squared. Okay. So it's 75. Okay. Then I'm going to say plus 5, and I'm going to square my 5. So 5 squared equals 100. Okay. Oh, this is looking good. And so that says r squared then equals 100 meters squared. And now I want to find r, so I'm going to take the square root of both sides. So say the square root of r squared and the square root of 100 meters squared. Okay, well, the square root of r squared is just r, and then I know that the square root of 100 is 10. I can take the square root of that. That gives me 10. Okay, so that worked out. So we did it correctly, and we got everything to work there. Okay, and um, this page right here. This is a good example of all the trig that we're gonna do in this class. Okay, and this is on the PowerPoint slide, but this is mostly the trig, right? Really, we're not going to do a lot more than this, and we'll do a bunch of examples in this, and I think there's some practice too. Okay, so let's go on then back to the lecture. Right. We looked at the trig. That was good. Well, let's go back to the PowerPoint. Okay, and we're on this slide right here. And here we've got the formulas. Cosine of theta equals adjacent over hypotenuse. Cosine of theta equals opposite over hypotenuse. And then tangent of theta equals opposite over adjacent. Now, notice in this slide here that my angle is up here. That's why this side is opposite. And that's important to remember because when you're doing this, it's okay to just turn your triangle sideways, right? If you know the angle of this upper one here, just man, turn your triangle sideways, okay? So we're saying it's adjacent to the angle, okay? And we'll do a bunch of examples. All right, but definitely review this. This is most of the trig that we're going to do. So the important thing to remember is make sure your calculators is in degrees and not radians. And if you get something crazy, go back and check. All right, so okay, here's an example. What is the length of the hypotenuse of this triangle? Okay, well, we don't know what the angle is, so we can use the Pythagorean theorem for this one. So let's just go do it really quickly. All right, so I'm gonna draw. So I'm going to draw a picture, a diagram, and I would say if you're doing physics problems, always draw a diagram. Okay, it doesn't have to be beautiful. I love to draw, but man, you can just draw boxes and squares. But the act of drawing it actually helps you to understand it because you're engaging different parts of your brain and it's very useful. Okay, so I'm drawing a picture before I do anything because I want one side is 6 meters, the other side is 8 meters, and it says, what is the hypotenuse of our triangle here? Okay, so we talked about this already. We're going to plug this into our Pythagorean theorem. Definitely, we probably have used this, hopefully before in algebra in high school, maybe pre-calculus, super important. Even the Greeks knew this one. This is a timeless equation. Okay, so we've got r squared, and I like to when I solve these, I like to just write down the equation in symbolic form before I do the problem. Right, just on your paper, write down the equation that you're going to use, and then put in the numbers because there's a temptation to just immediately start plugging numbers into your calculator. And one of the problems with this is after a while, you might get confused about what was on your calculator and what was where you are in the equation. What I always do is I forget to hit clear, and so it'll multiply it by whatever I had in there before. Okay, those are just really simple things that can help you not make mistakes. Okay, because there's going to be mistakes, and that's okay. All right, so we've got 8 here, so this is 8 squared plus over here 6 squared. Okay, so 8 squared is 64, and then 6 times 6 is 36, and this is r squared over here. Okay, and so now I'm going to take the square root of both sides. So I'll take the square root of this side here and the square root of that side. Well, 64 plus 36 is 100. Okay, so this is the square root of 100, and then the square root of r squared is just r. And this was actually the same problem, basically. Really similar, different angle here on our triangle, but we didn't know the angle. So that gives us r equals the square root of 100 is 10. So the answer is 10 meters. So I'll say, okay, r equals 10 meters. Okay, now. Uh, another thing I would say is, get a notepad and write this on paper. Get a nice notepad, and so as you're going through this, right, you can just fill this up. And I like these spiral ones. And you can go back and look at what you did. Okay, so here's all of your equations. You can go back, see what you did. And you know what the great thing is about paper? You don't need the internet and you don't have to plug it in. You don't have to charge it. Oh man. Okay. So definitely get some paper. Okay, so we figured this one out. The correct answer is C. We got that one. All right. So reading questions. Uh, People always ask me, oh, I'm not sharing my screen. Dang it. Okay. Yeah, there we go. Share my screen. Get rid of this window. Okay, so we're going back here. All right, so we saw here's our triangle. The correct answer is C, uh, 10 centimeters, right? And 6 and 8 are the sides. We just ought to do that. Okay. So, uh, at this point, hopefully you should read chapter one. Right? To this, it's in the module. Definitely do the reading. Um, so the thing about the reading is there's a lot of useful information in the book, and I've seen a lot of physics textbook and a lot of physics textbooks. This one is good. It's a great book, so definitely read it. A lot of the information is in there. Now, maybe you don't read every single word, but you should definitely check it out. These PowerPoints are basically a summation of everything in the book. Okay. And I'm going to go through this. I'll try to make these videos quick and give you the information that you need. And then there'll also be some problem videos. Okay. But hopefully, if you haven't already, you've had a chance to look at section 1.1. That's what this video is about. Just a couple of pages. So read it real quick. Maybe read it right now. Come back to it. But all right. So I'm assuming you're going to stop and look at that part. But what is the difference between speed and velocity? Okay. Those are two different things, similar, but not quite the same. Okay. So what is the difference between speed and velocity? Okay. Is it A, speed is an average quantity when velocity is not? Um, uh, Not really. Averages don't really matter. I mean, there is such a thing as an average velocity, but that's not the key difference. Okay, B. Well, velocity contains information about the direction of the motion while speed does not. Well, that one looks pretty promising because yes, absolutely. Velocity does have a direction and it has a magnitude. Okay. Speed doesn't have a direction. Speed's just a number on your speedometer when you drive. It's based off of how fast the wheels are turning, but you don't know any direction. Okay, C, so B looks good. C, speed is measured in miles per hour, while velocity is measured in meters per second. Uh, I'm gonna be honest, in physics, I would not use miles per hour for any. Fact, I would just forget all of the American measurement systems. I'm going to post a video about those. But everything should be in meters per second, whether it's speed or velocity. For the purposes of this class, we use meters per second. Now, I say that I remember there are some problems where they give you a number in miles per hour. Sometimes it's okay, you can get away with it, but man, if you have to convert, just go with meters per second. Okay. The concept of speed applies only to objects that are neither speeding up nor slowing down, while velocity applies to every kind of motion. No, that's not true. An object can have a speed and a velocity, whether it's speeding up or slowing down. Speed is used to measure how fast an object is moving in a straight line, while velocity is used for objects moving along a curved path. Nope, no, that doesn't make any sense. Okay, so I think we agree that velocity contains information about the direction of motion, while speed does not, and that's the important thing. Speed is a vector, and no, speed is a scalar. Oh my goodness, speed is a scalar. Velocity is a vector, so it has to point in a direction. Okay. Significant digits. We just talked a little bit about those. We're going to do more with those. The quantity 2.67. 67. 67. I have a teenager. Um, Here's our quantity. It's 2.67 times 10 to the 3. The question is, how many significant figures does it have? Well, Um, hopefully you know that the answer is three, um, uh, and not four. And that's really important when you're doing calculations, okay? And when you enter your answers into the software, you have to do significant digits. That's important. Now, when you're calculating things, you don't want to throw away those extra digits when you're in the middle of your calculation. Okay. Wait till the end and then round off. And we're going to talk a lot about this. Okay. But this one has three. It's 2.67. Since it has three digits here, you have three significant figures. That's the rule. Okay. Now, if this number was 2.670, they add that extra zero on the end, then you know that's okay, that's four. Okay. But this one has three. So the correct answer is C. All right. The correct SI units for distance and mass are A, foot pounds. Oh gosh, no. B, centimeters and grams. C, meters and grams, or D, meters and kilograms. Well, hopefully you read this first part and you know that in SI units, the standard units are kilograms and meters, okay? And we don't use feet or pounds for anything in physics. Okay, so meters and kilograms. Um, Grams are okay, but when you're doing your calculations, you just, as a default rule, switch to kilograms. Okay. All right. If Sam walks 100 meters to the right and then 100 meters to the left, his net displacement vector is what? What direction is it? Well, okay. He said he walks 100 meters to the right. Oh, and let's, you know what? Let's make a video about this. Oh, okay, you know what? Because I have some, I've been waiting to use these. Let me show you what I got here. Yeah, there it is. We're gonna, I don't know what I'm said here. Okay, so Charizard. Yeah, Charizard. Let's read the problem. Okay. I think physics is more fun with Pokemon. Okay. I don't care if you like Pokemon, I like them. It says Charizard goes 100 meters to the right. Okay, so he's gonna go to the right 100 meters. And we're gonna say that each one of these squares is 25 meters. Okay, so Charizard goes 100 meters to the right. And so he's over here, he's at 100 meters. We're gonna call this position 0. Okay. And then after he was 100 meters to the right, he's going to go 200 meters to the left. Okay, so he's going to go back here, back to 0. That's 100. And then he's going to go over here. And so Charizard's going to end up over here. Okay, so his net displacement, it looks okay. Here's where he started. He started at 0 and now he's 100 meters to the left. And so I'm going to draw my net displacement vector is going to be this pink one. Okay, or oh, it looks red on. Oh no, it's red. Dang. Okay, I have a pink pen too. But his net displacement is minus 100 meters. And what direction is it pointing? It's pointing to the left. Okay, because we say the negative direction is to the left. So let's go back here to our problem. And all right, so it's points to the right, A points to the left, C has zero length, or D cannot tell out more information. Well, it's pointing to the left, right? We can see that from our picture that we drew. Charizard ended up to the left. Okay, he's right there. There we go. So it is to the left, and the length of that vector, the magnitude is 100 meters. There's Charizard. Okay. Velocity vector. Velocity vectors point in what? Is it A, in the same direction as the displacement vector? B, in the opposite direction as the displacement vector? Or C, perpendicular to the displacement vector? Or D, in the same direction as the acceleration vector? Or E, velocity represented by a vector? Okay, so velocity vectors point in the same direction as the displacement vector. That sounds usually reasonable, but let's look at a couple of examples here because all right, so let's say let's get, oh, here's Pikachu. Oh, yeah, Pikachu. All right, let's say Pikachu starts over here. Right. Oh, and we'll retrace right there. Okay, so usually let's say here's our origin. Okay, and if Pikachu starts here at the origin, okay, he could move over here. How far did he go? Let's say each square is 25 meters. Okay, and so let's say he's over here. He's 250 meters over here. Okay, 250 meters this way. Okay, so his displacement vector's over there from the origin. That's where Pikachu is. He started over there. Right? Now, what if Pikachu starts heading back to the origin? Right? If he starts going this way, right? Which way? Well, his velocity, his displacement vector is over here, but now his velocity vector could be pointing back that way. I think for a lot of cases, though, as let's say Pikachu goes this way, if he's moving that way, then his velocity vector is going to be pointing in that direction. Okay, so let's see what the answer says. Okay, in the same direction as the displacement vector. Yeah, that's usually true. It's not in the opposite direction of the displacement vector. Although I always think about what if he's moving back to the origin? Okay, I don't like this slide. I should just delete it, but whatever. Okay. So the important thing is, and we're going to talk about it to define this, is where's your origin? Hey, where are you calling zero? If I say x is zero this way, if I say x equals zero right here, okay, his displacement vector is how far is Pikachu away from the middle here, right? He moved 250 meters. And now you have to decide which way is he moving, right? Is he moving more negatively? Is he moving more positively? But let's say, because if he's moving towards the origin, uh, yeah, we'll see that his velocity vector is the change in displacement divided by time. Okay, so we're going to talk more about that. But all right, let's go back to the presentation. We want to get through this is just going to cover 1.1. All right, so motion is a change in the object's position or orientation with time. Okay, so things might be going in a curved path. Uh, how do they move over time? And they in the book they call this path the trajectory. How did the particle move? Okay, that's its trajectory. The path that and motion is a change in object. Okay, so here's a motion diagram. They use motion diagrams a lot in this book. Very useful. And we've got three different kinds of motion. Okay, in the first one, right, if we say, all right, I'm riding my skateboard and it takes a picture every zero point 0.1 seconds. Okay, the distance between each of these, it doesn't change. Okay, so here's my displacement vector. Here's this the change in direction. This is the same every time. Okay, all these arrows are the same. So this is constant motion. Now in this one, okay, I'm drawing the distance between each of my runners here. That's one. And then over here, my final one. So you'll notice that these displacement, the change in distance here is increasing. Okay. And so that means that she must be speeding up. She's accelerating, right? Because the distance between each of these positions in time is increasing. Now, this one down here on the bottom, here's my car. So from the first frame to the second frame, my arrow looks like this. Then on the second one, it looks like this. Okay. And over here, it looks like this. So my arrows are getting shorter. That means it's slowing down. Okay. So it says, yeah, the skateboard's moving at a constant speed. The runner's speeding up and the car's slowing down. And here's my basketball. Erase all this stuff. All right. So my basketball here, there's two kinds of motion. There's motion in X and Y. And when I throw my basketball, okay, my basketball is moving this way. So it's moving over here this way. And what's interesting in the X direction, it's constantly moving by the same amount in time. It has its velocity doesn't change as you go forward. So its forward velocity is the same. However, uh, its y velocity is different, right? So as you throw something up, right? then it starts to move up, but then after a while, it doesn't go up anymore because it hits the peak of its motion, and then over here it starts to go down, right? And so the y motion changes, but the x doesn't, and our x velocity remains constant. We're going to do a bunch of problems like that, okay? But in time, the x velocity doesn't change, y velocity does change. Okay. Here's a my car. Okay, so motion diagrams are made of two cars, both have the same interval between photos. Which car A or B is going slower? Well, on the left here, we can measure this. Okay, so here is my line. Okay, so this pretty good. And then over here, okay, the distance between those two cars is it's a lot higher. Okay, and so which car is going slower? If I compare these two, right, then my two lines, the distance between those, car B is much bigger. So car B is going faster. And so yeah, car A is going slower, right? I just drew a line there and I compared them. So it's going to cover more distance. Car B is faster, but it is moving to the left. So it's got a negative velocity. Remember, negative just tells you about the direction. It doesn't tell you whether it's going slow or fast. Okay, so that's a big difference between velocity and speed. Okay, now, all right, so that's the end of this video. Just a quick video, section 1.1. When you're ready, go to section 2.2 if you want to. You can put me on fast forward so I sound like a high pitched chipmunk. So maybe I'll talk deeper so I sound normal in here. No, I'm not gonna do that. I'm just gonna talk normally. But although if I talk deeper, if you watch me in fast motion, then it might sound normal. I don't. I'm not gonna do that. All right, thanks for watching. And I'll also post some videos. Actually, let's do a problem now. No, and let me talk about yeah. So this is the end of section 1.1. And let me talk about the homework a little bit. Okay, so here's the plan for the homework. The homework has I think there's 18 problems in the first one. And so my plan is that I'm going to do 4 or 5 of those on the videos so we can do them together. Okay, so each homework I plan on doing several of them on a video and so that we can go through them kind of together. Okay. So thanks for watching this video. There will be lots more videos.